Hey guys, bonus video here, still on 10.3. I wanted to do at least a couple more puzzles with you guys. We're picking up from one that I did in class and also on the main video, right? But there's an easier way to solve this, right? So, question we're looking at is if you have these seven numbers, 222, 3357, what's the probability of arranging them exactly in that particular order? And the catch is that, well, these first three twos you could actually put in any order and it wouldn't actually change the outcome, right? So I went through okay, logically, and I walked you guys through this, right? And then we're looking at the math after the fact and realized, hey, there's actually is a pattern here, right? And that is, right, so we're looking at it, 7 factorial would be how many ways could you arrange it if they were all unique, would just be 7 factorial, right? And then the chance of any one arrangement will be 1 divided by that, right? But the fact that these three twos are the same, that leads to 3 factorial, and then these two threes are the same, right? That's 2 factorial, right? There's a single 5 and a single 7, so 1 factorial is just 1 that shows up, right? Right, so there is a simplification here, right? This was actually the very first question on your Alex, right? Now you guys had different scenarios. Let me zoom in here a little bit. Right? Different scenarios. Here I have 14 cans of food on a shelf. Some of you guys had groups of politicians that were going to sit, and they were in like 3 different parties, so they were equivalent politicians if they were in the same party. Some of you guys had there was a word that was spelled, and it had multiple letters that were saying how many different ways could you rearrange the letters. Since we're looking at cans of food, let's stick to this one. So we have these 14 cans. We have 5 cans of olives, 1 can of carrots, 8 cans of beans. How many different orders can be arranged if 2 cans of food are considered identical? So you cannot distinguish these 5 cans of olives, for example. You could switch them all up and you have no idea which is which. So all the 5 cans of olives are the same. Okay? So here, jot it down. See, 5 olives, 1 carrot, 8 beans, 5, 1, 8. Okay? So let's bring that over here. Okay, so we have 5 of one type, there's olives, right, 1 carrots, and 8 beans. Yeah, and those do add up to 14. So I'll say the sum of the cans equals 5 plus 1 plus 8, which is 14. Okay, and so how many different ways could you rearrange this? Right, so a number of arrangements. Okay. Well, if they were all unique cans, then at face value, it would just be 14 factorial because the first can could be any one of 14. The second can could be any one of the 13 remaining. So it'd be 14 times 13. And the next, well, now there's only 12 cans. You have 14 times 13 times 12, all the way down to the last can would be 1. So it would be 14 factorial. But in this case, since these 5 cans of olives are indistinguishable, I'm going to divide by 5 factorial. Okay, because that order doesn't matter among those. Right? I have 1 with carrots, that's 1 factorial, which doesn't really change anything, but 8 beans. So look like that. Now, you could spell this out because you guys know 14 factorial is 14 times 13 times 12 times 11, and so on, all the way down to 3, 2, 1. Okay? Or in a calculator, remember you can go to PRB and you can scroll over and you can choose that factorial right there. So I'm going to put that in parentheses, divide by, then keep here, open parenthesis right there, because I got to group all these together. 5 factorial, well, 1 factorial, which doesn't really change anything. 1 times 1 is just 1. And then 8 factorial. Right, so I typed that in exactly, and I'm getting 18,018 different ways to arrange these cans. 18,000 something different ways. Okay. Now, if you turn this into a probability question, like what's the probability that the first 5 are all olives and then followed by carrots and then followed by the 8 beans exactly? The chance would be 1 out of 18,018, right? There's a 1 in 18,000 chance of that, right? Let me show you guys that that will be the answer. Right. So I type 18018. It should tell me this is correct. Let's just make sure here. Yeah, that's exactly what I'm looking for. And while I got Alex up, there's another one I want to look at with you guys. Let's do number 9. Right. Again, there's different scenarios for these. Here we got a deck of 10 cards. Some of the guys had one that was like there was a wheel that they were rotating like a pinwheel or something. Right, so 1 through 10. He's playing a game of chance. The game is this. Lamar chooses 1 card from the deck at random. Remember, there are 10 cards. He chooses 1. He wins the amount of money equal to the value of the card if it's an odd number card. He loses $5 every time it's an even number card. What's the expected value of playing the game, expected value. Okay, so okay. Now this one I'd like to draw out. Let's see, he's gonna win the amount if it's odd. Okay, lose $5 if it's even. Okay. Okay, so I'll draw the 5 cards. We got card 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is the card number. Right? And then what will he win if he draws that particular card? Okay. Well, if it's odd, he wins that amount of money. So he wins $1 here. So these will all be in dollars. Okay. He wins $1, $3 if he draws the 3, $5 if he draws the 5, $7 if he draws the 7, and 9 for the 9. Okay. But all the evens, remember, he'll lose 5. So I'll call it -5, -5, -5, -5, -5. Okay. Now, if you played the game 10 times, because there are 10 cards, right? You draw or you don't know which one you're gonna draw. But hey, what's like the sum of the values, right? So sum of the values, I'll do it that way. Okay. Well, um, you could add all these numbers up. Remember, positives and negatives would subtract from each other. Okay. But I can also kind of look at it this way. I'm going to point out all the winnings, okay, and the ones I didn't put to would be losing. Okay. But what's the average of the winnings? Well, here it would be 5. 7 and 3, the average of that's 5. 9 and 1, the average is 5. Right. And there are 5 ways to win. And the average loss would be -5, and there are 5 ways to lose. So if you add up all these numbers, you can do it on the calculator. Okay, what I said, you hit 0. Okay. So the expected value of any one drawing would be the sum of the values, which $0, I should say, okay, would be $0, okay, and then divide by the 10 draw, because he's only going to draw once. This is like if you add all the numbers, but that'd be like if he drew 10 times, right? It would take him 10 drawings to draw all these, at least 10 drawings, right? So we're going to divide by 10 because he only draws once, but it's still 0, still 0, right? Now, there are variations on this. So if you change the numbers, you might get some expected value. Like if I added up all the numbers and it added up to 20, I'd say 20 divided by 10. And every time he draws, on average, you could expect 2. Because if it was like $20 if they sum 2, I'm saying if, this is a different scenario, right? Okay. And 10 cards, I would say you would expect $2 per draw, right? So then if you did 100 draws, right, so then 100 draws at $2 per draw, so times $2 per draw, right, you could expect there to be $200 in winnings, expected value. Okay. Again, it won't be on the nose. Right? Sometimes it'll be less than that. Sometimes it'll be more, right, for drawing 100 times, but the overall average would be. Okay. Now, this is just something I just made up. Okay, but this particular value we're looking at should be 0. So let's go back over to Alex. I'll type in $0. So per draw has to be 0 on average. So in the long run, okay, yeah. So now if he plays this game 100 times, well, he's gonna expect to approximately break even, right? Approximately. Okay? He might gain a little, he might lose a little, but 0 times whatever would be 0, right? Can I? Oh, here we go. Check. Let's make sure it gives it to me here. Yeah, right. That's exactly what they were looking for. All right, so there's a couple extra examples.